on this course related to the Neutron diffraction. So today we will have the second session, tomorrow the third, and also the last one. And we will have a coffee break from 4 to 4:10. Okay, we will share some biscuits and coffee. And thank you so much for joining. I hope that you will enjoy this session. Please, Dr. Mohammed.
Thank you, Dr. Yana. Okay, so we can continue with the second day, and today I will show you some applications for the Neutron diffraction. So as I mentioned yesterday that I'm a metallurgist, so basically I will be showing mostly about alloys and with their thermomechanical behavior. Okay, so so we can revise what we have seen yesterday. What is the main difference between X-rays and the neutrons? And when we do diffraction with X-rays and neutrons. So X-rays basically interact with electrons, while neutrons, because of their neutral nature, they interact. They directly go to the nucleus and they interact with the nucleus. And because of their heavy mass, they can also give us bulk properties. And as we have seen yesterday, that with for X-rays, the cross-section increases linearly with atomic number. So it would be very difficult to detect light elements with X-rays. While with neutrons, they are very good for light elements, and they can also distinguish between isotopes in addition to having high penetrating power. And we also seen that the main aim of doing diffraction doesn't matter if we use X-rays or neutrons or electrons. We want to see atomic arrangements. That's where everything is. And for that, it is always Bragg's law which governs that. With the neutron, the only difference, okay, there is differences, but the main difference is why we like them so much is because they can really be helpful for gauging bulk behavior because they have high penetration power. And these are some figures. So if we use lab X-rays, where we use copper K for target, and its wavelength is around 1.54 angstrom, and it can just penetrate up to 10 micron. So basically, we'll be just looking at the surface. If we go to synchrotron, which is high energy X-rays, there you can get maybe up to 100 microns. But with neutrons, we can go up to 10 millimeter, actually more than maybe 10 millimeter, depending on which kind of materials we are looking at, depending on their composition, and because cross-section depends on a specific element. So this is the main reason why people sometimes love to do X-rays, because sometimes, neutron diffraction, because you cannot obtain information with, say, X-rays or some other means. And we also talked about different sources of neutrons yesterday. And one source is nuclear reactors, which is kind of steady state. It will have continuous production of neutrons, but neutron yield is a bit low. And we have detectors, so these neutron comes and they interact with the sample, and we have information or patterns in this way. The other method, which is now more popular, is time of flight, which we abbreviate as just TOF, which comes from pulse-based sources, or we call them spallation neutron sources, because they operate in pulses. So we will have a pulse of neutrons, and then stop, then again next pulse, and so on. And in this, because it's a pulse and there will be neutrons of all kind of energies and wavelengths will be coming out, so we call them white neutrons. So we'll have a range of wavelength for these neutrons. So they interact with sample and then we detect them. But there, how we obtain information from here, it is a bit different compared to how we obtain from lab X-rays or by this method. Here we use time of flight, which means how much time it takes for neutrons to reach from their starting point until we detect them in a detector after they have interacted with the sample. So by knowing that, so everything else is known. So basically there, I mean, if we look at this equation, this is very well-known equation, like how to obtain that. So this is moment. So this is L is length of from source of neutrons to the detector. So that's the distance which they have to travel. Remaining are constant, Planck's constant, for example. So basically we substitute this thing in this equation, in Bragg's law. When you do that, so you just substitute it over here. So this is what you obtain. So G spacing, Planck's constant, m is mass of neutron, L is distance from target, source to target, which is source is neutron source, and the target basically is detector in this case after they interact with sample. So this is constant, mass of neutron is constant, L is also constant because for a specific beamline or specific instrument, they keep their distance same. So it may vary from instrument to instrument, but for the same instrument, no matter whenever you do experiments, it's going to be the same. So this is, and also I will show you how the arrangement is usually done. So theta is also always constant, how they align their detector towards and their sample and their source. So the only thing which is not constant is this G and this D. So what we obtain from Neutron diffraction from, or in specific, in this case, from spallation or pulse sources, we obtain T, which is time of flight for neutrons to reach from a source to the detector after they have interacted with the sample in the way. So when we get that time, then by just using this formula, you can convert it to T spacing or lattice spacing, right? And that's what we're after when we construct these diffraction patterns. Okay, so I also shown you because of specific kind of requirements, every neutron source can have specific beam lines, and that can depend on which kind of materials you want to study, which kind of properties you want to explore. So you can, if you want to do diffraction, there can be, for example, engineering materials diffractometer. Almost all the sources have this instrument, which is most important for us people working in the metallurgical engineering field. And then there is powder diffractometer, especially for texture analysis. Then I mentioned about small angle neutron scattering if you want to get information at large scale, like on macromolecules or in dispersions, kind of solutions of supralloys. Then you can also have imaging, radiography. Then there are different kind of inelastic skating instrument. So depending on which kind of materials or which kind of phenomena you want to look at, you have to go to a specific beamline, and they somehow, their source is same, but somehow they operate independently. So which kind of information we can obtain? So we have to think like where we can find applications for neutrons. So we can start with the simple one which we all are familiar with, which is crystal structure analysis. So what we do both for single crystal as well as powders. So the main advantage for using neutrons is detecting light elements. For example, hydrogen or lithium, which we know that are difficult to detect by X-rays. Then one of the very famous thing for neutron diffraction is residual stress measurement, which is again, we can have scene profiles inside, especially these weld joints, because when we do welding, we know that there should be some residual stresses. So that is very, you can obtain it very accurately by neutron diffraction. And again, advantage comes from their deep penetration, which cannot be possible with X-rays. Then another thing is we can do elemental analysis. Again, okay, here it should not be boron, it should be lithium, I think. So again, we have, when we have to detect light elements, then it's a good way to do that. For example, hydrogen, lithium, etc. Then if you want to do, I have shown you some images yesterday, radiography differences between X-rays and the neutrons. And it is very now popular to do that by neutrons. So for example, this enclosed container and you want to know what is inside, and especially if it has some organic substances, then that can be easily done without breaking this container. And especially for people who work in archaeology, for them it's very important that we want to have non-destructive analysis. So for that, it's very helpful for doing imaging. Then sometimes people also can take they build some devices and they want to see their, evaluate their behavior. They can also take that to neutron sources. Then you can have laminated structure by small angle neutron scattering. Then you can have dynamical behavior, which I mentioned that this is about inelastic scattering. And you can do that different kind of spectrometers by, for example, for phonons and magnons and so on. And then also another thing is about macromolecules or biological substances. They can also be studied, and there are specific dedicated beam lines for that purpose. Again, because they contain mostly carbon or hydrogen or something like that, which can be very easily detected with the neutrons. So because it have high penetrating power, and you can do it non-destructively, and you can detect light element. So that is the main reason why people use neutron. So these are some of the applications, like illustration, like which kind of things people can do. This is, of course, which residue stress measurement. You can take whole like bulk piece of pipe or maybe whole wheel of a train, and you can just put in between the detectors, and you can do it to see residue stresses inside. So in this case, it's almost half a meter diameter of this tube. Then I mentioned yesterday about radiography. So you can see like how good you can, if it is enclosed even inside some container, you can see it very accurately. Then of course for crystal structure, then different kind of proteins, magnetic structures. Okay, so now I will mainly be talking about mechanical behavior and which kind of information we can obtain by using neutrons. So when we have, mostly we deal with polycrystals, and we have different arrangement of grains, different arrangement of different orientations for grains. So what we basically do, I mentioned about small angle. The wide angle is diffraction, basically what we do with the XRD. So we have grains which are oriented in different direction, right, in different ways. And when we apply stress, and we get some, or without even before applying stress, we get some peaks, right, which is as some specific lattice spacing. So this is crystal structure. So what will happen when you apply, say, stress? Which kind of things can happen? For example, we are applying tensile loading or compressive loading. So one, the peak can move, peak can shift, because when we apply tensile loading, so we are stretching the system, right? So what we are doing, basically we are stretching lattice. So there will be expansion, there will be, so until, of course, everyone knows that until elastic limit, it can be reversible, but beyond that, it should not come back. So when we do in situ loading, which means we put tensile machine in between neutron source, in between neutron beam, and then we start loading it, and then we'll see which kind of changes are happening. So the peak will shift. In this case, it's tensile loading, so the spacing will become larger. So this is because of the strain change. So dimension will distort for this lattice. Second one, peak can become broader, right? So why that will happen? Because of different sub-grain structures, which is grain refinement, but it can also be main reason, like during deformation, is because of dislocations. Dislocation density become larger, and that's why we have peak broadening. And the third one is intensity change. So you see its intensity have changed. So this is the original peak, is position shifted, is width change, is intensity change. So intensity is basically related to texture. If your material have texture, then of course it will have different, it will not have perfect, normally we go for random texture. But when we do deformation, then grains rotate towards some specific orientation. I will show you some examples which orientation they prefer. Okay, so these are the three kind of things which can happen when we are doing loading, and we are seeing which kind of changes are happening. And from this, everything we can estimate. about dislocation density, about planar force, about volume fraction change, and so on. So I will talk a little bit about intergranular strains. So we have three kind of stresses or strains which can be happening within a polycrystal. So one is macroscopic stress, which we just obtain as such, like it's the overall response. The stress in curve is macroscopic behavior what you obtain. But when we are doing experiments on polycrystals, so we also should remember like there should be interaction between grain to grain. So there will be stresses coming from there as well. So that's what we call type 2 stresses or intergranular stresses. Actually, we use interchangeably stresses as well as strain. But here, like they are referred to intergranular stresses. So which will be between this one kind of family of grains and the other family of grains. And then there will be also stresses within grains because of different kind of substructure, different kind of defects, for example, dislocations or crystallites within the main grain. So that we call type 3 stresses. But mostly what we deal with is type 2 stresses, which is grain to grain, and we will see how that works out. So this is just an illustration of an instrument where we use powder sample, or powder sample mean like it's polycrystal. That's what we usually call powder sample. It's like have no random texture. So we have sample in the middle, and then we have this detector, and we have neutron coming from this side, and then ultimately we get something, and we'll see which kind of changes are happening as a result of stresses. So one final family of grains will be like, because it is time which it takes from source to the detector. So that's how like this spacing will work. So first one you will have first peak, which will be maybe 111. That will be one family of grains which will be gaining information about, right? So this is the same thing, but like we have different family of grains, so they will have intergranular stresses, and their magnitude is just shown here. Okay, so again, same thing. So usually this is what if we look under microscope, this is what structure looks like if it is kind of equiax grains, more or less. And then we can have different family of grains, right? So you can see that over here is 111 kind of family of grains, and blue here is 200 family of grains, right? And when we do diffraction, this is for stainless steel, so this is FCC phase. So we have peak for 111 at this T spacing, right? And then we have 200 and then 311 and so on. 220, 311, 400 and so on. We have specific grain on it. So it's a combination of all of these 111 within the whole aggregate. That's what this peak is coming from. And this is how we know texture information. So what we obtain over here is grains which are normal, whose plane are normal parallel to the diffraction vector. So, and which is defined by instrument geometry. That's what we obtain in the detector. And of course, each grain of family of grains will contribute a distinct peak. For example, these grains for 111 and at a specific interplanar spacing, a D spacing, right? Okay. So this I just mentioned that we use time. So I will be now talking mainly about pulsed or spallation sources. That's what now mostly people are using. So that's why I'll be using time of flight many times. And now I think everyone knows what is time of flight. The time which it takes for neutrons to travel from source to the detector, and they interact with the material in their path. Okay, so neutron beam is coming over here with the different wavelengths, interact with sample, we obtain it over here, right? And it follows the same Wegg's law, but in this case we modify it with the momentum, right? And ultimately we have the spacing versus time of flight. Everything else is constant, including angle between this sample and the source of neutron. So this is how it looks like. So we have a sample which is usually for these kind of experiments is 45 degree to the incident neutron beam. So neutrons are coming from here. This is a slit to control the beam size. they interact with the sample over here, right? And then we have these two detectors, which are usually 90-degree apart. So 90-degree apart from the source actually. So one is plus 90, the other one is minus 90. So one of them we call, so the one which is minus 90, that's usually from where we obtain information about the loading interaction, because our sample, just consider about tensile sample. So we have loading axis and we have transverse axis, right? Or radial axis. So loading axis is where we are pulling it. But if we don't have that kind of thing, then we can just assume like, okay, this is axial traction, the other one is transverse traction. For example, if it has texture, then it will have different kind of peaks in these two detectors. So this is a really good way to look at both loading traction and transverse traction, or axial traction and radial traction. Right. So when it interacts with the sample, then we have those family of grains whose normals are parallel to the beam. We obtain specific reflection for them. So in this case, you can see different kind of grains, grain families, and we can get different kind of grains. Okay, everyone awake? Any questions? It's good so far? Okay. Okay, so basically this is the principle which we follow in neutron diffraction throughout the experiments, and mostly you will see this kind of setup which is used. Okay, so for example, it have two phases in this case. So you can see for phase center cubic and the body center cubic, you have different reflections. So this is what you obtain at the end. Okay, any question? Okay, so what we are mainly interested in, as I mentioned about intergranular stresses. So what we are interested in, how different family of grains respond as a result of stress. Now I'm talking about behavior under stress. So when we apply stress on a sample, this is, by the way, loading, tensile loading. And when we apply stress, how different family of grains will behave. I've shown before that how we obtain these peaks. But then we can obtain something called lattice strain. So lattice strain is basically, I have shown you that when we apply stress, then the peak position shift. This is as a result of lattice. I mean, lattice is under stress. So as a result of that, we have lattice strain. So basically, this is initial position and how much it changed during loading. That is for lattice strain. So this is when there is no load. We start increasing the load, and you can see different family of grain. So you can straight away see this is 111, right? This is again FCC 304 stainless steel, and this is along the loading direction. Transverse direction should have negative lattice strain because of balance of Poisson effect. So 111 have the highest lattice strain if we look at them at the same stress value, while 200 have the least, these circles over here, which tells us that 200 are compliant grains, compliant reflection, compliant orientation, because you can develop more. You can like easily move them even by applying. They can develop like less. It is the other way around. So 200 have the higher lattice strain at the same level of stress, while 100 have less, right? So it means 200 will develop more lattice strain, so they are more compliant, which means they can easily be rotated, while 111 are more stiff. So you can obtain, so this is during elastic region, and during elastic you can see like they are almost linear, but somewhere in yielding you can see like they divide from linearity. For example, this one was linear, and then it become non-linear. But it can happen at different, it doesn't follow the same macroscopic yield stress, because when we're looking at, we are doing tensile testing, so we have one yield point, right, where it deviates from the linearity. But that is accumulation of all kind of grains, right? But here we are looking at individual family of grains. So some of them can deviate, will yield first than the others. So during elastic loading, elastic for a specific family of grains, they will be linear, but after that they will become non-linear. And from this linear behavior, we can find Young's moduli for each family of grains. Okay. Any questions? Okay, it will come again, but of course I have to repeat it a number of times from the beginning. Okay, this is what I mentioned. The initial linear spread is because of elastic anisotropy. You can see like they are not at the same point because they have different, most of the material which we deal with, especially metals and alloys, they are anisotropic. While some of the materials, they are perfectly isotropic. But in this case, they should have some anisotropy, so that's why they are not at the same point. So that's why some of them are more compliant and others are stiff. So that's why, until their elastic limit, so that's because of elastic anisotropy. But the further spread which happen after that, that is because of plastic anisotropy. Okay, so now I can show you which kind of equipment usually you see when you go to do this kind of experiment. This is one of them. No, usually they are known as engineering materials diffractometer because that's what their function is. So in this case, this is a machine, loading machine. Normally in our labs we have vertical loading machine, but here because of the space they design their own machines, which is usually horizontal. So this is the driving axis. So you can apply load from this direction, and sample will be in the middle. While these two are detector banks. As I mentioned that one of them will give us information about loading direction or axial direction. The other one will give us about radial or transverse direction. And usually, so this should be 45 degree to the neutron beam. So neutron beam will be coming from here. I don't know if you can see east over here. So beam will be coming from this side. And this is 45 degree to the neutron beam. While these detectors, so they are 90 degree. So this is minus 90 to the beam, and this is plus 90. Clear? Okay, this is just close up of the machine. So because I mostly work with cryogenic deformation, so that's why like I usually show this setup, because this is for cryogenic loading machine. Because for room temperature loading, we don't enclose it. But for cryogenic, we have to enclose it, and we have to create vacuum as well, so that neutrons won't interact with the air inside the chamber. So this is a huge chamber from the other side, and this is here, like you cannot see it, but this is from this side. So this slit, this hole which you see, this tube, so this is basically neutrons coming from this side. But can you see that this is enclosed chamber, and there is a window, and this window is made of vanadium. So this whole chamber is made of steel, because it has to be very strong, some stainless steel, particularly maybe 316. But you can see there are two windows over here, one over here, one over here. And similarly, there will be one window on the other side. So this window is for this neutron beam, which is made of vanadium. So the reason is because vanadium don't interact with neutrons. So that's why they can without any interaction, they can just pass through it, and they are aligned on the sample, and then they can interact with sample. Because if it will be made of like steel as such, then neutrons will interact with steel, and what we will get will not be from the sample which we are studying. Sample can be anything. Similarly, these windows are for aluminum. From this side as well as the other side, they serve the same purpose as well. Aluminum also have different kind of spec and cross section. So this is for detector. So when neutron have interacted with the sample, then they have to scatter, they have to diffract. So they are diffracted from this window to this detector bank, and similarly there will be another window on the other side. And as I mentioned, so this is axial detector, and this is a radial detector. And this is just mechanism like we cool down with GM cooler, and this is vacuum chamber, and so on, and there is a vacuum tube. Okay, and this is how the sample looks like inside this chamber. So because this is at low temperature, so sample is here, and this is in between these sample jigs or holders, and because we have to cool it down, so we connect. So GM cooler is here, and its bottom is this one. So this is at around 4.2 Kelvin because we are using liquid helium for this one. So then through these copper wires, it is connected to this copper beacon grips so that it can ultimately cool sample. And we have sensors, SUNOX sensor or thermocouples we can also use, so we can do sense temperature, how much is temperature over here. So this is just to show you setup. So we can put like very, very huge machines in between neutron beams to study their behavior. So this is the schematic which I mentioned, the mechanism which neutron diffraction follows. So we have neutron beam coming from this side, this red. Then there is a slit to restrict its size. Usually we use, so that it depends on like usually like they have 2-3 configuration for their own convenience, and then it will interact with this sample. So usually what we use is 5 millimeter by 5 millimeter. It can vary, but for this kind of study specifically, I'm saying usually that is the size. So your sample like 5 by 5 millimeter, that will be totally under will be interacted with neutron beam. So it interacts with the sample, which is over here, and we are applying load, right? We are stretching it. And those grains whose normal is parallel, whose diffraction vector is parallel, they will be diffracted in this detector. And those diffraction vector is perpendicular, they will be diffracted in the other detector. So we get axial information about the axial direction as well as transverse radial direction. Okay, now we can talk about some specific topic like where we can use this kind of technique. So, for example, one of the most important field is automobile industry, and we know its different components are made of different kind of materials, different kind of structure, different kind of phases. So one of the most common material which it uses is trip steel because of its very good properties, strength as well as ductility. And also it has some of the part are we need shock absorption so that when it collides, so it will not immediately collapse. So it have to have that kind of capability. And for that, trip steel is one of the best thing because when you apply stress, so it will transform to another phase. So in this case, there is arsenite can transform to martensite when it is under stress. And it can have very good properties. You can see UTS, ultimate tensile strength and elongation, and the usually trip, because of the trip effect, its name also you have transformation. So arsenite transforms to martensite. So martensite is usually stronger phase. So because of that, it have higher strength. But the thing which we want to understand by doing in situ experiments, especially neutrons, is how different transformation the phase center cubic structure, when it changes to say martensite, how it contributes to strength. We want to understand that. And how, so for that we do neutron diffraction. And what is this deformation pathway? We also want to know that. So this is one of example you can see with the neutron diffraction. So this is d-spacing, and these like smaller numbers, they are d-spacing. This is 2 strain. And you can see these are the peaks marked over here. So this is the starting zero deformation. So it was pure phase center cubic structure, so gamma phase. So you can see they are marked 111, 200, 220, and so on, right? It was single phase. But once we started deforming it, at some point you can see this peak coming up, right? And this is HCP. You can see it is indexed over here. Similarly, this peak, this is also HCP, right? And then this one. These are very weak peaks. And then at some point, you can see another kind of phase is appearing, which is epsilon prime, which is BCT. But in this case, BCT is very close to BCC, so usually it is considered similar to BCC because its tetragonal axis is not that different compared to cubic. So then this phase start, right? Then you can see peaks coming for this alpha prime over here. So they start at a specific time of loading. So you can really pinpoint at which time, when how much deformation you need to activate this transformation, and then how much further you need to go to activate another phase. And after, also you can see around the end, you can see epsilon phase or HCP phase almost is disappearing, right? So you can also get that information. Okay, it means it is transforming to a different kind of phase. In this case, this phase appears, but from FCC. Similarly, BCT also appears from this one, but ultimately this one also transformed to BCT. As I was mentioning, we have usually information about two detectors during loading. Sorry, there is a typo. So this is loading reaction, and this is transverse traction. Transverse mean which is across normal. So in this case, here in the first one, you did not see anything over here. If you go to the transverse traction, you can see there is a very tiny peak. So sometimes because of texture or some kind of specific principles, you can maybe miss information in one detector bank, so you can obtain it maybe in the transverse traction and vice versa. So this is very helpful. You can really see the whole mechanism which is happening. Usually what we do, we do deformation and then we take sample to say XRD or TM, and then we try to find out which kind of physics those are. But here you can have this information throughout the experiment. And then we are also interested in how much contribution each phase can have to the stress, overall stress. So here from this information, we can have phases, phase fraction for each of them. And so this is the stress incurred at very low temperature. So these relations are because of very, very low temperature. And then you can see contribution from each phases. This is from Neutron data, while this is macroscopic stress, this is a black curve. So gamma phase, which is FCC, epsilon, HCP, and then BCT. So you can see that gamma almost disappears at the end. Epsilon appears, but then it also is consumed by, and ultimately is the BCT, which is basically giving it about lot of work hardening. So that's the main contributing phase. So we can estimate stress value for each of them. Okay. So next I can talk about high entropy alloys. So these are a few examples which I'm giving you, like, okay, for example, for steel, people are working in steel, and we want to know like when transformation happen and what is contribution of stress for each phase. So if you were already here yesterday, I talked about high entropy alloys in the seminar. I can just quickly mention like what they are, and then I will show some results from Neutron diffraction. So for pure metals or alloys, so pure metals, of course, they are single phase. For single kind of atoms, alloys we add some substitution elements, but they are in small quantity, and we have a base metal on which this alloy is based. Steel is an example. We have mainly iron, and then we add something to improve its properties. But high entropy alloys are usually multi-component systems. So they can consist of 4, 5, 6 kind of element in maybe equal or near equal proportions. They may or may not have minor additions, and at the end you can have random structure. So you have to remember that when we say disorder and order structure, that's very important. Remember what we are talking about that. Disorder, for example, when we compare crystalline versus amorphous, so amorphous is disorder, right? It doesn't have any structure. But this is a different kind of disorder. This have crystal structure, but the arrangement is random, arrangement of atoms. So it's compositionally is disordered, but in a structural way, it is ordered. Order means it have crystalline phase. And it can specifically people anticipate that it can have properties or applications for very advanced applications because they can have a very unique properties, especially their strength and ductility and toughness and magnetic properties, superconductivity, number depending on which alloy you are studying. So one of the applications people are pursuing is about tokamak or fusion reactors, and another one is for aerospace. And also these are the applications which usually happen at low temperature. So when these alloys, when there was this paper which was published and which really made high entropy alloys popular was when they tested this alloy at room temperature. Of course, it was ductile; it had 45% ductility, which is quite ductile material. It had good strength. But when they defined it at low temperatures, below room temperature, 200 Kelvin, you can see increase in ductility as well as strength. But when you go to further low temperature, you can have significant increase in strength as well as ductility, which is not what we should expect usually. Because when we deform most of the alloys, either they can become completely brittle, mostly BCC alloys or metals, they are brittle. And one of the best example which we can quote is sinking of Titanic. Titanic did not sink because it collided with a glacier. It sank because it fractured into two because of ductile to brittle transition. They were using, I think, cast iron, which become very brittle at low temperature. So the temperature was very low, and it just fractured because of that. It's split into two parts. For FCC systems, they usually retain their ductility. They don't have ductile to brittle transition temperature, but their ductility always decreases at low temperature. They are still ductile, but for example, if I have to take steel, stainless steel, for example, 304 or 316, its ductility at room temperature will be okay this much, then its low temperature can be somewhere over here. It will be ductile, but still lower than room temperature. But in this case, they saw that its ductility is very high, so they want to know why. And this is what we are after, why they have very excellent properties at low temperature, especially ductility, and what is the deformation mechanism. That's what decides mechanical properties. So I mentioned these examples yesterday as well. This is called Cantor alloy, which consists of 5 elements, consecutive elements from a periodic table, and 20 atomic percent each of them. So it's equiatomic high entropy alloy. And so when we take these 5 elements, they consist of different kind of crystal structures. Iron and chromium, they are BCC. Nickel is FCC. Cobalt is SCP. Manganese is, you can see, very complex structure. But still, it can, when they combine it in different this way, they can still form single phase and cubic structure, which is against Hindothree rule. So they break that rule. But this is because of they have high entropy, confusion entropy. So if you remember this equation, it gives free energy. So it's enthalpy of mixing minus entropy of mixing multiplied by temperature. So because we make alloys at high temperature, and if they have high configuration entropy, then Gibbs free energy can be negative. But still, like, you also have to look at enthalpy. If some elements have very high enthalpy, then there is still chances they will not form solid solutions. Right. So this is what we did like 5-6 years ago with this alloy. So we wanted to know, there was already this study at 77K, which I shown you. They went up to 77K and they saw an increase in ductility. So we were interested in what will happen if we go to further low temperature, the lowest possible which we can do. And we wanted to understand its deformation mechanism, deformation pathway, and what is the reason why it have high ductility. So we did the neutron diffraction experiments, and as I've shown you that this is the instrument which we used, and this is cryogenic loading chamber, and this is how sample look like in another configuration. And so we did at 3 temperatures. So of course, room temperature, 140 Kelvin and 15 Kelvin. And you can see with every successive decrease in temperature, the strength increased, but also ductility increased. So strength almost become double at 15 Kelvin compared to room temperature. But ductility also increased significantly from almost 46% to 62%. Now, but at low temperature, I did not mention this yesterday. I can just briefly mention that these are called serrated. This is happened because of serrated deformation, which is a kind of a characteristic behavior at low temperatures. And whenever this happens, there is always a peak in temperature as well. So this is a separate subject. So maybe if anyone interested, we can talk about that later. So we saw like at 15 Kelvin, it's the similar behavior, the ductility increases. And also we saw the sample at 15 Kelvin deform more uniformly. There was no necking as such. And we also looked at, we were expecting there to be phase transformation at such low temperature. That's what happened with steels, for example. Also mixed in steel, by the way. But in this case, we have diffraction pattern at room temperature, before loading at 15 Kelvin, and then near yielding, and this is near ultimate strength, almost here at the top. And you can see this was FCC. These all peaks belong to FCC. So by the end, you can see, of course, peaks like they shifted, they become broader, they become their intensity change, but overall it remains single phase phase. This is along this phase. So see, it will change single phase structure. So nice another kind of a thing why, because people did simulation, they thought like they predicted that there should be phase transformation, but we did not see any phase transformation. So, but as you can see, mechanical behavior increased, ductility also increased even at 15 Kelvin, and there was no phase transformation in this case. Then we looked at its texture and the stacking fall probability. So stacking fall probability is what are the chances of making stacking falls. And I think, as you know, that stacking fall happen when dislocations separate into partials, and they are separated by these stacking falls. So we can obtain this information by doing these kind of in situ experiments. So upper panel is blue circles, squares are for room temperature, and the red triangles are for 15 Kelvin. And you can see stacking fall probability is almost zero. I mean, it does not increase. While for low temperature, it starts increasing from here and then it continues increasing. So there are a lot of stacking falls which are formed during this process. And as I mentioned that intensity change means texture change. So you can see that for room temperature, which are these pink or purple, I think. I don't know, I can't see color properly here. Anyhow, these squares, they are for room temperature and it's continuous change in texture. So this is by the way 111 for load interaction. And from Taylor's models, we know that when if deformation happens by dislocation slip, then the grain should rotate towards 111. No, actually it's other. The 111 grains should rotate towards load interaction, while they should 200, for example, or 220, they will be a bit away from the load interaction. So that's why this intensity should continue to increase. This is what happened at room temperature because it is mainly by dislocation slip. But at low temperature, you can see it's increasing, but then like there is no change at the end. So it means something else is happening, and we can know that it's because of stacking fault. So the texture changes in a different way. Okay, you can see that, but there is still dislocation slip because at least during like first part. So in this case, at room temperature, it is only dislocation slip, while at low temperature, it's both dislocation slip as well as stacking faults. And as I mentioned about texture change for 111 orientation, so that is this difference is because of stacking faults. And we also looked by TEM. As I mentioned yesterday as well, that we usually just don't rely on one kind of technique. We somehow have to complement with some other technique as well to give additional proof. And especially if you are trying to prove something, then you have to like to show that okay, no, it's also can be seen by other methods. And here we can see that so these are at room temperature, very few twins and mainly dislocations, but at low temperature, so these 4 images are low temperature, 15 Kelvin. So there are some stacking faults, and then twins, and at high resolution image also show these twin boundaries. This is a selected area diffraction pattern, it is very small, so maybe you cannot see, but like there are additional spots, which is because of tuning. So we have this hexagonal because of FCC, and then the additional one should be because of stacking faults, twin fault in this case actually. Okay, I think should we stop here?
¿Tienen preguntas? Pueden preguntar en español o en inglés.
This is for break. No?
Do you want a question and answer session?
Yeah, sure, we can have question and answer session, and then we can have break and we can continue.
Pueden preguntar cualquier cosa en inglés o en español. ¿Alguien tiene preguntas? Por favor.
Okay, so are they as dangerous as X-rays? For example, they, when you are imagining yourself, or they are imagining you, they go to a different room just to avoid getting too irradiated. Is there a similar thing with photon beams?
Oh yeah. Okay, good question. Yeah, of course. Actually, so each instrument is enclosed in a room, and they have a very thick concrete shielding. So Dr. Liliana came to Japan. This was in Japan in December. I was there for 3 months, and she know that it's very thick concrete walls around the whole room. And before starting experiment, they have an interlock. You must close. They have a very huge sliding door, like I think it's 30-ton weight. So they have a mechanism and interlock for that. So unless you close that gate, you will not be able to open the beam. So once you close that gate, all the locks are set, and then it will allow us to push button. Okay, now I can start experiment, and now neutrons can come to the instrument. So no one can be inside until that, and everyone who enters, they have to take a key. So it's a physical key. So you take in, after like you have finished work, you come out, you put in the key, all the key, like they have like 6, 7, like how many people are going in. And from one place, then these keys should be like take another key from there and then to go to a different place, and then you close the door, and once like everything is at its place, then you can really push the button. Okay, now beam can start. So yeah, of course it's dangerous. Of course you have to take that kind of precautions. Yeah.
¿Alguien más quiere preguntar algo? ¿En inglés o español?
While you are thinking, I can also say that I am collaborating with Dr. Liliana and some undergraduate students are working with me. Actually, Dr. Liliana is supervisor. I am co-supervisor, and we are working on different kind of alloys, including high entropy alloys, and mainly with neutron diffraction. So if you are interested in any kind of collaboration, and if you don't want to do any project, you should talk to Dr. Liliana because she's here. I will be here for tomorrow, but then I will go. So you should talk to Dr. Liliana and discuss if you are interested in anything, and we can do collaboration or we can do some project. That would be very good.
Thank you. Somebody else? Some questions? No? Okay, I just want to ask you first. In your graph of first strain and then first strain, I think it was a alloy.
Yeah.
I'm just curious, you have, at 15 Kelvin. I just want to know that kind of consideration is because of the holding time for measuring neutron diffraction, or is something related to what the image anterior?
Yeah, that's excellent question. Yeah, so it's not due to holding time because this is specific mechanism which happen at low temperature, serrated deformation. It can also happen at other temperature, but for low temperature, it's very common. You will see in all kind of alloys, specifically at very, very low temperature. And yeah, it is due to PLC, what you are seeing, effect, and this is because of dislocation dynamics. How dislocation, because at low temperature they have different kind of behavior. So they are kind of like trapped at one point, especially when dislocation density is high, and then ultimately they release. So suddenly there will be low drop, and then they pile up again. and then again like this process continue. This is kind of avalanche which happened. So it's because of that.
Thank you. Any more questions? No? Okay, so we can proceed to the coffee break. There is some coffee and cookies waiting for you. And then we can go back to the things. Okay? Thank you.
That's good. I was like, okay, you can finish your discussion first. Okay, so I will very briefly go through which kind of information we can obtain when there is no phase transformation, for example. And I shown these figures yesterday in the seminar that what we obtain, most of characteristics for different mechanisms, they come from these diffraction peaks, right? So how they change during deformation, during loading. So this is the example at 3 temperatures. And this is just evolution at lowest temperature, 25 Kelvin. And you can see a single phase FCC. Of course, there is some peaks disappeared at the end. That's because of texture change. Because 200 grain, the peak which disappear over here, because these grains move away from the loading direction. But in transverse section, they will be stronger, as you can see over here. So that's how texture works. And so you can see we can obtain different kind of information, and I mentioned yesterday that we can peak shift and peak broadening and peak asymmetry. We can obtain different features, but this is very simplistic. This is just okay, stacking faults from here with the peak shifts, dislocations from peak broadening, then asymmetrical broadening because of twin faults. But this is very simplistic because these things does not exist in vacuum, doesn't exist individually. So they are interrelated. So we have to fit them in certain ways to obtain these kind of information. So this is kind of like a signature, but not in this simplistic way. Okay, so I want to emphasize that they have interconnection. So you have to kind of deconvolute these features. So from this we can, as I mentioned about lattice strain, which is kind of fingerprints for polycrystal materials behavior under stress. So I will show you for 4 temperatures over here. So room temperature, as I mentioned before, that 200, which you can see here, red filled circles, they develop the largest lattice strain. So they are the most compliant one. And 111 and this 220, they are the least. So they are the most stiff. And 311 is usually unaffected, so it's in the middle. While you can see these two are overlapped, right? When you go to low temperature, for example here, you can see remaining stuff. Of course, this value will change because room temperature have lower stress compared to say 140 Kelvin. So of course, this value will change, but you have to see like how their behavior changes. And one thing you will notice that here, this black and this, I think, pink triangles, they were overlapping, almost overlapping, but here they separated. And when you further go to low temperature, you can see like they separate from very beginning, and the separation is larger at the end. These two are very close temperatures, so you may not see much difference. So the reason for showing this is that from this kind of analysis, you can obtain stacking fault probability, which I have been mentioning for so many times. So from lattice strain and how these two be split, because 111, which is over here, black one, and 222, because they are parallel planes. They belong to the same family, but with higher order. So 111 and 22 is higher order. Similarly, 200 and 400, they belong to the same family of planes, but with different order. So they should have similar behavior as at room temperature, but they don't at low temperature because of stacking faults. Because we know stacking fault energy decreases at low temperature, and that's why we have stacking fault probability become higher. And then we can also obtain information about, so this is what I was mentioning, that stacking fault probability at 4 temperatures. And this I plotted with 2 stress. The reason for this is you can see that, I don't know how clearly you can see that the room temperature terminates over here, the black one, black squares. Then 140 Kelvin is blue circles, which terminates over here. While 40 and 25 Kelvin, they go all the way up to this value, around 5%. which is 50, which will be 5%. So the point for showing this is that the stacking fault activates at the same stress level for all of them, and the value is around 860 plus minus 20 megapascal. But the reason they cannot go further at room temperature because room temperature have lower stress. I mean, you have seen stress in curves, right? But if you plot it with the two strain, then you can see their distinct behavior, right? Because strain is like larger for these, so they can be separated. So you can see at low temperature, they are the most effective. The highest value we obtain at lowest temperature. Then at 140 Kelvin and 295 Kelvin at room temperature, it's very, very small value, just 0.5%, which is almost negligible. And also from this decumulation analysis of diffraction peaks, we can obtain dislocation density. And I will tomorrow mention about data analysis, and I will show which package we really use for this kind of data analysis. So here I plotted dislocation density with the two strain. So you can see dislocation density become very high at low temperatures, and that but they are quite similar for these two temperatures, 25 Kelvin and 40 Kelvin, right? And the value is almost 9 10 power 16 per square meter, which is very, very high dislocation density, especially for phase and cubic structure. So this is the reason these alloys have very high strength at low temperature, and they have a high ductility because they can generate more defects like planar faults, second faults, and twin faults, so on. Then we can also obtain twin fault probability. So both stacking fault and twin fault, we categorize them as planar fault, while dislocation is line fault, right? So they occur as a plane, right? We can also obtain twin fault probability for these temperatures by using some software package called convolution multiple fault profile method by using this Neutron data. And you can see twin fault probability at room temperature is almost negligible, very low. But at low temperature, it is almost 6% at 25 Kelvin. But here you can see that the difference between 40 and 25 Kelvin is significant with regard to twin fault probability. So what Dr. Ileana was asking about this seriation behavior, if you remember that it had like low drop and then recovery and then again. So here we think that dislocations interact with the twin faults and somehow they are blocked. And because twin fault also occur as kind of low angle, kind of like grain boundary, they can also behave like that. And because of that, maybe dislocation will be piling up against them. And once like they can cut through these twin faults, then there will be stress. Suddenly the stress will drop because they can have easy flow. But then again, they will encounter the next barrier, and then again a compilation started, and then again stress increases, and then again the process continues. So the point for showing this is that you can obtain dislocation density, stacking fault probability, twin fault probability, and lattice strain as I shown before, and also you can estimate which kind of texture is developing, at least qualitatively. And here this just with two strain, we can also estimate hardening contribution from each kind of mechanism. So this is what you have seen so far: stacking fault, twin fault, and dislocation density for 4 temperatures. And we can estimate how much each mechanism contribute to by using in situ experiments with neutrons. We can also do with the synchrotron, but synchrotron may not have these kind of environments. So this is up to yield strength. Of course, the main contribution coming from grain boundaries, dislocations, initial dislocation density, and if you remember, I was just talking about lattice friction stress or pulse stress, which become very high at low temperatures. That's why materials have very high strength at low temperatures. And after yielding, so dislocation contribute. This I just shown at 1 temperature, which is 40 Kelvin. So here, so dislocation density have significant contribution. It remains the main deformation mechanism, but dislocation stacking fault also contributes significantly. But at room temperature, the contribution will be very small. Here I just plotted at 4 temperature, and you can see contribution from dislocation density, which is the yellow one, after yielding. And this is from planar faults. And you can see at low temperature, planar faults contribute more. but still distribution density, distribution slip remain the main prominent mechanism. Similarly, we can also see if there is some kind of transformation. So in situ, we can see when does it happen. I will not go into detail because I think we don't have much time. And also we can relate it to, so this is again HCP transformation in chromium cobalt nickel alloy. And we can relate to development of, this is intensity, right, for FCC 220. And this is volume fraction, which is changed for FCP. And this is stacking fault probability. And we can correlate it with a mechanism that when stacking fault probability start increasing quite significantly, then we can have transformation to HCP. As you know that when stacking faults occur individually, then they can be layers of defects in FCC structure, right? And we can consider them single layers of HCP, but we don't call them HCP. But when they become regular and they accumulate, then they transform into, then we call them HCP. That's the main difference between stacking faults and HCP within FCC structure. And now I can talk about another topic, which is about shear memory alloys, because they have very superelasticity in these kind of materials. You know that for most conventional alloys, we have a yield limit, a yield stress, which is less than 0.2% of strain. This is what we are familiar with, right? And then there will be deformation, and there will be necking at some point, and then ultimately fracture. But we had a number of applications where we really need a lot of elasticity, a lot of elastic. I mean, we need metals or alloys, but they should be elastic. And springs are one of the examples. And I think, let's see how much it can go. So this is just a demonstration of like how much, because if you have elastic behavior, then it should come back to its original position. So it's like it can bend so much and still it can recover its shape. So it means like it is deforming elastically. So this elastic energy which was restored. And this was a publication just last year, where they used Neutron diffraction to see if it is really elastic or pseudoelastic behavior. And you will know that by looking at diffraction patterns. If their peak can come back, like it, when you apply stress, so the peak moves. But under elastic, this peak should come back if you release it. But under plastic, if it deforms permanently, then it should not come back. So that's what they did in this study. And they also found that their alloy have like so it was single crystals of copper, aluminum, manganese, and they compared with other kind of alloys, which had like 2%, which is also large, but they had almost 4.3% elastic strain limit. And also, because you can notice another thing, because it has very low Young's modulus, which is very good for biomedical applications. We are always after low modulus materials so that they can correspond to modulus of elasticity of bone. And they claim that it's like very low elastic modulus as well for this alloy. And another example, again, they used Neutron diffraction to do that. I will show diffraction pattern later. That they were thinking if this kind of deformation happens, it was almost 14.5% or 17% in these two kind of alloys, which is cobalt, chromium, aluminum, some silicon. The only difference is you can see is exactly the same alloy except for like 1% chromium cobalt going from one side to the other side. And they could recover it, but they were not sure if it is really elastic, superelastic behavior, or is it pseudoelastic behavior. And they were comparing with other alloys, and ultimately they did Neutron diffraction, and they wanted to know like why they can retain, if it is really elastic deformation, and if they can like recreate this hysteresis. So they did Neutron diffraction experiment. And you can see, okay, this is just, I don't know, it is that. So they did loading, right? And they did unloading. And you can see like these peaks, like how it shifts, but then it comes back when the load is totally removed. This is for transverse traction method. So you can see here. So this is start from here. Loading. It is being loaded. This is the point. And the peak is shifting, right? to higher despacing. And then they instead start unloading. You can see peak is going back. And when they completely unload it, so it is exactly at the same position as where it started. So it means it is the elastic behavior. And similarly, you can look at data stream. So by the way, this is for loading direction. In transverse direction will be opposite, because in transverse direction, when you are stretching it, so transverse direction, it should contract, right? That's what we see. So it was going to lower despacing, and when they started unloading, it came back to normal position. And similarly, latest chain was also recoverable, 100%. So this is loading direction, loading, which is this red one, and blue one coming back, unloading. And similarly for transverse direction, which is in negative. And this is the tactical C by ratio. So the point is, it was 100% recoverable, so which means it is a really elastic behavior. And they could really see it by a neutron diffraction and by using really big samples. Okay, and of course they did not see any phase transformation. Another example, the last one I think we should have is we can do thermomechanical processing of steel or any other kind of alloys in situ. So when we are cooling, so we heat up and then we start cooling, so recrystallization and other kind of things which are happening and transformations. So we want to know, excuse me, their starting point and which kind of transformation is happening and how long it takes, because it's very helpful for optimizing properties and then for applications. So here what they did, they put a furnace, like I have shown you a loading machine, but here they put a furnace and a loading machine, loading machine inside that furnace to heat up these steels. And they applied pressure, and then they could see deformation. So you can see high temperature deformation and how the phase transformation is happening when it is being cooled as well as heated up, cooled down, and during deformation, during compression. Okay, so I think I can just summarize over here that which kind of information we can obtain during in situ deformation using neutron diffraction. So mainly we are after lattice spacing, how lattice changes during loading, during cooling, heating, when we apply magnetic field. This is all about lattice change. So we have polycrystals. If they have texture, of course, we can have anisotropy deformation, and if there is phase transformation, so this is like maybe a 973 at we go to high temperature. So ferrite transform to arsenide. So we can see this kind of transformation at in situ at that temperature. We don't have to. Otherwise, it's very difficult because we cannot put furnace inside, say XRD or inside T, and we cannot really heat up at that temperature. And the main information which I have explained in last few minutes, which was about if we apply stats, so the lattice expands. So lattice because of stasis, that can be residual stasis, or maybe it is because of some solid solution atoms. Then texture can happen. Grain can obtain because of texture or because of twinning. Okay, so this should come from peak position. This is from peak intensity, and from peak width or shape we can have lattice like dislocations or stacking faults. And it should be planar faults, which is mainly twin faults. And of course, if there is phase transformation, then we should have new peak, or its intensity will differ. Okay, I think I can stop here. And tomorrow I will discuss about the data analysis methods, and it will be maybe a bit boring, but still we have to do that. And yeah.
Thank you for the excellent presentation today also. Do you have some questions? English or Spanish? No questions, comments?
Sorry. In one slide, you show the contribution of the H mechanism. Was 40 Kelvin. Yes, maybe it's about other topic, but how do you know the contribution of which mechanism. Because in the graphic, you show that the elastic zone is one mechanism, and when we apply the load, you show other types of mechanisms. Or how do you know which mechanisms are?
So we go step by step, because you have to get this kind of information first, right? And that you obtain from peaks, like their position, their broadening, their symmetrical broadening, and so on. So when you have this information, you can do this. Then you can estimate how much is coming from that. So I think you are relating it to some other, topic, another method, I think. I'm not sure, but anyway, the point is you get this information from peaks in situ when you are applying load. Then from that, so this you obtain by fitting, which I will discuss tomorrow, by reticle refinement, by this method called convolution multiple fault profile method, which we normally call profile fitting, so that you can estimate how much this percentage value is coming from there, or this distribution density is coming from there. And then further we have equations. So we can use, this distribution density, then we have to use equations to get this value. Because I did not put the whole table. So if you are interested, of course you can also talk to me, but you can also read this paper, which is a bit long paper, but you can also read that. It have all the details, including those equations. And here I just simply shown that, okay, you can obtain this information, but to get to that point, you have to travel, certain areas. Okay. So you have equations where you use moduli and you use lattice parameters and other factors to get this kind of information.
¿Alguna otra pregunta? ¿Inglés o español?
Yeah, so maybe it's a good play, but do you need any kind of preparation, for example?
Sample preparation. Right. So the simple answer is no, but always there is a but. It depends which kind of information you want to obtain. And of course, if you want to do tensile loading, you have to have a tensile sample. If you want to do, say, high temperature compression, you have to have that kind of specimen so that it can fit in the sample holder. But if it is just you want to look at structure or something like that, then you don't have to prepare a sample like what you do with TEM. That's why TEM is amazing, but the issue with that is sample preparation is really, laborious work. And also, most of the things which we do with this kind of method, they are non-destructive. But of course, if you are trying to do, say, loading study, or you trying to heat it up, of course, you have to apply those things. But if you are just looking at structured people, as I was mentioning, that sometimes they just take a wing of aeroplane and they just put it on the sample table. It's really huge, maybe this big, at least half of it. You just put it over there and they may raise residual stresses. Similarly, they can do with the giant wheels of trains. So for that, no, you don't have to do any preparation. You just put it over there and you just start from there.
What's the cost of applying these techniques to a specimen?
Sorry, could you repeat? I could not get it.
What's the cost?
Cost.
Of applying these techniques to a specimen?
Okay, very good question, because always money matters. Okay, so I mentioned yesterday that you can get these experiments done without any cost, zero cost, because they are publicly funded. Wherever you have, wherever they have these facilities, say in US, in Japan, in China, in Europe, anywhere. If you want to do it for research purposes, non-commercial research, and you want to publish it, it will be free of cost. But you have to write a proposal for that. They have, every facility have, I can share maybe a bit tomorrow about that, but I can just very quickly say that every facility opens proposal calls twice a year. And anyone can, from any field, if they think it can be helpful for them, they can submit proposals. They have specific layout for that. And it's like very small proposal, like you have to write maybe 2 or 3 pages, that's it, it's not very long. But in that, you have to prove that your research is really worth doing with neutrons, number one. If it is not like worth, then no one will be interested in that. Second, you have to prove that you cannot get this information by any other methods. For example, how the question was if we can do it without destroying material. For example, if the material is like you cannot destroy it, you cannot do destructive testing, then of course maybe this is the only option. So it's free if you are doing it for research. But if you want to, they also provide commercial. If you want to do for say industry, that is very, very, very expensive. Because these are really billion, or maybe I think approaching $1 trillion facilities. So they also offer a commercial one in which you don't have to publish, you don't have to disclose anything. It's up to you. So industries do that. A lot of automobile industry, a lot of aeroplane industry, aerospace industry, they often like acquire their services. So does the steel industry for residue stress measurement, for example. So if you are doing for research, like how I think most of us are here, it's no cost, but you have to submit a proposal. So they will send it for review, similar to how you do for funding proposal or for research papers, right? So they send it for review and it will be peer reviewed. And after that, they can obtain comments, then they will reevaluate. And then they will set a panel to decide like how much time you can get. It's very precious time, that's true, but it's free of cost if you can like fulfill those criteria.
I have another question. It's how many time does it take to make this technique just one specimen?
You mean how much time it takes to measure one specimen? Okay, that depends what you're measuring. If you are measuring just structure, what you're measuring, and what is composition, and how big is your sample. These 3 factors in that order. So if you just want to measure structure and say steel, say austenitic stainless steel, maybe a few minutes, that's more than enough. But if you're measuring something, say you want to do deformation experiment, for example, this low temperature one, it takes whole 1 day. Because you have to set up experiment, because machine, like you cannot take your own machine. You can actually take your own machine, but it's not easy. Especially if you have to take from here to say another country. So it needs time to cool, setting up specimen, closing chamber, making vacuum, then cooling it down to the lowest temperature, holding it for some time, then starting loading, right? Then experiment finished, then you have to let it cool down before you can open it because it's under vacuum. So it can, if now like they made like a bit better because only 2 facilities have low temperature facilities for doing this kind of experiments. But now you can do maybe 2 samples in a day. But again, it depends. What is elongation? If it is like say 10%, you can finish earlier. But if it is like 90%, it will take longer time. And usually they do experiments very, very low strain rate. Because I mentioned yesterday that neutrons are a bit slow. So you have to accommodate certain statistical counts so that it can be like good quality patterns. So depends what you're measuring and what is your purpose to measure, like which kind of properties you want to measure. So it can be from few minutes to maybe a day.
Thank you.
You're welcome.
¿Alguna otra pregunta? ¿En español o en inglés? ¿No? ¿Preguntas, comentarios, traumas? ¿No? Okay. So I have a question.
Okay.
One is I think you show one study that I think is not yours, if I'm not mistaken. But it's a study in which they study the phase transformation at high temperature, but also I think it was during the cell test, if I'm not mistaken. So my question is, how can you separate the contribution of temperature and strain for phase transformation? Because I think they occur at the same time.
You mean this one?
Yeah, I think yes.
Okay. So, for us, yeah, that's a good question. How to separate it? I think it's difficult, but because in this case we are mainly concerned about thermomechanical processing, right? We want to optimize both temperature and the deformation parameters. Like you can think it in a way of, for example, how you are doing a high temperature rolling or high temperature forging, right? In that we apply both of those factors. So in this way, it's not, I mean, you cannot really separate it, which is coming from temperature and which is coming from stress. For that, you can do two different experiments if you're just interested in temperature effect and if you're interested in just compression effect. But in this case, because when we do any kind of thermomechanical processing, it involves both of them, temperature as well as stress. So ultimately, we're interested in which kind of structure we obtain. So mainly, it comes down to that. But no, we cannot separate. You're right.
Thank you. And one second question. You showed me one slide that I think room temperature and low temperature. You have similar distribution density. So that's pretty interesting. And I want to ask you, I know, you have studied the distribution density. What have you studied or are you studying the distribution arrangement? Like, for example, there is the vitals.
Right. So the thing is, when we use, because we obtain this information from, profile fitting, whole profile fitting. And this is a method developed by, I mean, it's an old method by Wilkins, but it was modified by Tamashunga, a Hungarian metallurgist. And what we do in that, you use different parameters. And it involves dislocation character, like with edge or screw, crystallite size, because when we are deforming, crystallite size can go down, it can become smaller. But it also involves a parameter of distribution arrangement. So I will talk about it tomorrow, and one of the factor for is dislocation parameter, the arrangement, distribution arrangement.
Do you have some other questions? So thank you so much. Do you want to add something?
No, I think that's it.
Okay.
Yeah, as I said before, that if you are interested in working, I mean, like you're interested in anything which I am working on, or like what you heard, so you are very welcome to approach me while I'm here. As well as I said, I collaborate with Dr. Liliana, and we have been working on different kind of materials. So if you're interested in collaboration, or you want to start a project, we'll be more than happy to collaborate with you. Thank you.
Thank you for joining for the second session, and